Everyone, welcome back, and today let's solve Leetcode problem 769 titled Max Chunks to Make Sorted. So we're given an integer array of length n that represents a permutation of integers in the range from 0 up until n minus 1. So we can split the array into some number of chunks, basically just partitions, and individually sort each chunk. And after concatenating the sorted chunks into a final resulting array, that result should equal the sorted array. And we need to return the largest number of chunks we can make to sort the array. And largest number of chunks is very important here because, of course, an obvious solution to any input, of course, apart from the empty input, would literally just be to use one chunk. So in other words, only have one partition. So in other words, we don't actually split the array into two separate things or anything like that. We simply just take the array as a whole and consider that to be one whole chunk. And obviously, if we sort that entire array, it would equal to the sorted of its regular whole array. And so one chunk would kind of be like the minimum we could get for every single test case here, but we have to try to get something that's more than one chunk, right? Use more partitions than just one. So as you can see in example 1, our input array is 4, 3, 2, 1, 0. And in this case, we really only can have one chunk. And the reason why is because if we actually make a partition to split this into two or more chunks, then we can't actually meet the required result to actually return or get a result of the final sorted target array. Right? And the reason why is because, again, splitting into two or more chunks is not going to return the required sorted final result. Right? And they also give us an example to see what would happen if we split it into two different chunks here with the one partition. If we split it into two different chunks, getting 4, 3 and 2, 1, 0, if we sort 4, 3, we'd get 3, 4. And if we sort 2, 1, 0, we'd get 0, 1, 2. And 3, 4 plus 0, 1, 2, those two arrays concatenated with each other would give us 3, 4, 0, 1, 2. And obviously, that isn't the sorted version of this entire array, and so that would be false. And for example 2, we have our input array to be 1, 0, 2, 3, 4. And in this case, we can actually make 4 separate partitions, or have 4 different chunks rather. And the different chunks we can actually split this into would be 1, 0, 2, 3, 4. Right? That's basically the two chunks that we can actually split it into. And so if we split it into two chunks, such as, again, 1, 0, and 2, 3, 4, that is going to be a possible solution. However, that is not the most number of chunks we can split it into. Because, again, even if we do split it into just two separate chunks with one partition, we'd get 1, 0, and 2, 3, 4, which would still give us the right result. However, we can do a lot better. We can make a lot more chunks, and in this case, that maximum is 4. And the way we could do that is simply just take this 1, 0, then just simply take this 2, this 3, and this 4. And notice how when we concatenated the sorted of all these different chunks, we get the result of the sorted of this, which is a 0, 1, 2, 3, 4. Right? 0, 1, 2, 3, and 4. Right? Which is obviously the resulting array that we want to achieve. So with that out of the way, I will give you guys a few seconds to just go over this problem in your head and think of a valid solution. And then I'll show you guys how I would optimally solve this problem in a few seconds. Okay, so to just quickly reiterate here, we briefly discussed at the beginning of this problem statement here that the minimum number of chunks for any test case would be 1. Because the reality is, even if we split this array into just one chunk, so we didn't actually make any partitions, if we sorted that chunk, we'd get the sorted of the whole array, because the whole array is our only chunk. And so we can only have one minimum chunk or 0 partitions for the minimum for every test case. But obviously, we want to maximize or get the largest number of chunks, and so that would definitely not be optimal, at least for most test cases. And so what can we do to optimize that solution? Well, the key to this problem is actually realizing, well, if the maximum value in our current segment of the array, if it's equal to the segment's index, well, then we know that that segment can actually form a valid chunk and be part of a valid partition. And so the way we're going to solve this is first just iterate over our array, and we'll do this while actually keeping track of the maximum value that we've actually seen And we'll do this in probably I'll just use a variable called max so far. I'm not going to discuss the actual low-level details about that just yet. But at each index, right, if our actual max so far, if it actually equals the current index, well, then we know we can actually form a chunk with it. And so we can actually increase the number of chunks to actually use for our problem. And of course, the way we can do that is simply just increment a counter chunks variable, an integer variable, each time we actually found a chunk boundary in each iteration of our for loop of our input array. So with that out of the way, let's go ahead and start diving into the problem here. So first of all, let me actually initialize my max so far array, or rather integer variable, sorry about that. And it's going to be initialized to 0 because of course we haven't actually traversed through our input array yet. But what is this max so far variable? Well, what is it actually keeping track of? Well, it's simply just helping us keep track of the largest number that we've actually seen so far at that iteration in our input array. Okay, and once we've actually initialized this max so far variable for every segment or potential chunk, now let's actually initialize the number of chunks to be 0. And this chunks equals 0, well, this chunks variable, well, that simply just keeps track how many chunks we can actually form from our input array, right? Very simple. We'll eventually return that as our answer, so I can actually have that right here if I really wanted to. I'm not going to right now, just to not overcomplicate the code right now. Okay, so well, now let's actually start iterating over our input array. So for I and num in the enumerate of our array, and again, we want to keep track of the index along with the maximum so far value at each iteration. That's why we want to actually enumerate over our array to keep track of the index and the value and not just the value itself with regular for loops here. And for anyone who hasn't really used Python before, this enumerating function literally just loops through this array data structure parameter, but along with keeping track of the number or the actual value at that iteration, it also keeps track of its index, which can be stored in the variable I as a second iterator. Okay, that's basically what the enumerating function does in Python for kind of like a high-level breakdown. And obviously, we want to maximize the value that we've actually seen so far in our max so far variable. So at this iteration, the max so far value that we've seen up until this index or this iteration for this potential chunk, we want to maximize that to, of course, be itself because we don't want to make it smaller. And of course, the current number num, right? But what are we actually doing here maximizing this max so far variable in this iteration? Well, in this iteration, and of course, in each iteration, we have to actually update this max so far to actually be the maximum of course, its current, because again, we don't want to make it smaller, and the value at this current index num. Okay, or rather at this current index I, right? We want to maximize it between that and the current number num in this iteration. Right? And basically that makes sure that this max so far is always going to be maximized, or in other words, it's always going to hold the largest value that we've actually encountered so far, okay, which is very important to solve this problem and potentially form a valid chunk. Now, if the max value that we've seen so far in this iteration, well, is if it's actually equal to the current index I, and what are we simply checking here? Well, we're simply basically checking, well, does the max value in this iteration so far that we've actually seen, does it actually equal the current index? And that basically just indicates that all of the numbers in this current segment from the start to the index, are they actually correctly positioned to form a valid chunk? And if that's the case, we can increment the number of chunks we actually need by 1. And effectively, once this for loop actually is done executing, we simply have to return the number of chunks that we actually use to form from our input array. And unless I'm adding any syntax errors here, they should be accepted. There should be a valid solution. And as you can see, this is just about as efficient as you can get. So, for a quick high-level rundown of how this code actually works, as you can see, it's pretty short and pretty simple here, at least relatively, right? Basically, as we actually iterate over our input array, right, basically, we're simply first maximizing our max so far variable to actually keep track of the largest number we've seen so far in this current iteration. And whenever the max so far variable, or rather value, whenever it actually equals the current index, that means, this is the key part here, that means that all the numbers in the range from 0 up until that index I in this iteration, that means they're all in their correct positions relative to their sorted array. right? That's where the sorting part comes into play. We actually have all the values in this range from 0 to I, which we can check in the max so far variable. And if that's the case, well, we can simply form a chunk, and we can rather increment the number of chunks we can actually form from our input array by 1. And effectively, once we're done actually iterating over all the different indices and their numbers in our input array, and actually checking all those computations, we simply have to return the number of chunks we actually counted at the end. So for the time complexity of this solution, this is going to be a big O of n solution. It's pretty straightforward here. The reason why is because this is really just a one-pass solution. We're really just iterating over our input array once, right? And of course, every single number gets chucked exactly once. And so this is going to be a big O of n, or linear time solution, right? And for the memory or space complexity, this is actually going to be a big O of 1 solution, or a constant time solution. The reason why is because we're not actually using any auxiliary memory or any extra data structures, right? Really, we only have like two integer variables, right? Chunks and max so far, but they're actually going to have a constant, or rather use a constant amount of extra space. And so the memory or space complexity is going to be a big O of 1 solution. So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.